Hey guys, welcome to a new video. In today's video we're going to look at a Leetcode problem, and the problem's name is even odd tree. So in this question we're given a binary tree named even odd, and it has to meet the following conditions. The first condition states that the root of a binary tree is at level index 0 and at level 1 their children are at level 2 index. So it says that the leveling starts from 0th index. And for every even leveled index, all the nodes at that level have odd integers in strictly increasing order. And the third and final rule states that for every odd index level, all nodes at the level have even integer values in strictly decreasing order, and the order is from left to right for both the conditions. So we are given the root of a binary tree and we have to return a boolean value as our output. We have to return true if the binary tree is even odd, which satisfies these conditions, else we have to return false. Now let's take a look at these examples and see how we can solve this question. So let's take the first example given to us. This is example 1. Now let's take a look at the three rules. The first rule states that the level starts from 0. So this is level 0. So this is level 1 and this is level 2, level 3 and so on. And this is the condition for even level and this is the condition for odd level. So let's mark them. This is the even level and this is also even level. This is odd level and this is an odd level. And finally we have to return either true or false as the output. So we know we have to iterate through all the levels, and this is a clear sign that you can use BFS so that you can iterate all the levels, and at every level you have to perform some operation. So I think BFS is a good choice for this traversal. So in BFS you maintain a queue. So initially you add the root into the queue. I'm only taking the first element and there is a left subtree and right subtree for every root. Now we are at even level. We have to check if the values present at even level are odd in nature and are strictly increasing. So keep track of a tree node which is initially null, and I keep track of the current node which we retrieve from the queue. So the current node is 1. So remove it from the queue and we have to process it. We check if it is odd. Yes, it is odd. And check if it has any other nodes in the current level. No, there is no other node. So this condition is satisfying for level 0. And now for the next iteration, and we keep track of the level. Level is initially 0. Now we have to go to level 1. Now how do you go to level 1? You add the left child. You check if there is a left child for this. Yes, there is a left child. So add it into the queue. Check if there is a right child. Yes, there is a right child, so add it into the queue. Now take the topmost element from the queue, that will be the current node, and pop it from the queue. Now we are at odd level. Check if that value is even. Yes, 10 is even, and compare it with its previous value. Now we have to check if it is in strictly decreasing order. So that is in descending order. If strictly decreasing, that is the current element. Now we access this. Now we have to compare. Now current will be here, and previous, which was initially null, should become this element. So update current value to previous. So previous will now become 10. And now check if 10 has a left child. Yes, 10 has a left child. So add it into the queue. Check if 10 has a right child. No. So you don't add anything. And now this becomes the current element. So this becomes 4. So pop it from the queue. Check if this is a even number. Yes, it is a even number. And check previous value is strictly increasing. Yes, 10 is greater than 4. So this condition is also satisfying. And now we have to update the value. This becomes previous. 4 will become previous for the next iteration, but now there are no more elements because we finished processing this level. And now we have to add its left child and right child into the queue. Yes, left child is there, so add it. Check if right child is there, so add it. And now go to the next level. So these two elements are also accessed. Now in every iteration, previous will become null. And now we go to the next level. So we are at this level now. And using this level variable, you check if it is an odd level or even level. And for every level, we reset back previous to null, so that we can start new level comparisons. Now take the top element is 3, so that will be current. So pop it. So 3 is the first element and check if it is odd. Yes, it is odd because we are at even level. Now this becomes previous, 3 becomes previous, and before going to the next element, check if 3 has a left child. Yes, 3 has a left child, so add it into the queue. Check if 3 has a right child. Yes, so add it into the queue. And now you pop the current element from the queue and this becomes 7. Let me rewrite this. Now check if this current element is odd. Yes, it is odd. We need odd element. Check if it is strictly increasing. Yes, previous was 3 and it is strictly increasing. So this condition is also satisfying. Now before going to the next element, check if 7 has a left child. Yes. Check if 7 has a right child. No. So don't add them. Previous element is 7 and current element is the topmost element 9. So current element is 9. So pop it from the queue. Check if this is odd. Yes, this is odd. Check if it is in strictly increasing order. Yes, the order is being maintained. So both the conditions are satisfied for even level. And now before going to the next element, check if 9 has a left child. No. So don't add it. Check if 9 has a right child. Yes, so add it. And before going to the next iteration, we increment the level and we reset back previous to null. And now we are at this level. Now the current element is 12. So take that. Check if it is even. Yes, because we are at odd level. Check if it is strictly decreasing. Yes, it is strictly decreasing. So 12 is the first element in the level. Now update previous to 12 and current element is 8. You don't have to add anything because this is the last level. And if you check left and right child, both are null for all the nodes in the last level. So I'm not checking them. So current node is 8. Check if it is even. Yes, it is even. Check if it is in strictly decreasing order. Yes, it is in strictly decreasing order. So pop that element from the queue. Now previous is 8 and current is the top element, which is 6. So pop it from the queue and check if this is even. Yes. Check if it is in strictly decreasing order. Yes. So both the conditions are meeting again. Now update the values. Previous will become 6 and current node is the top element from the queue. So 2 will be the current element. So pop it and check if this is even. Yes. Check if it is in strictly increasing order. Check if it is in strictly decreasing order. Yes. Both the conditions are satisfying again. And now increment the next level. We are going to the next level. So level is 4. But now the queue becomes empty. It means we processed all the elements once. And if we haven't returned false until now, if at any point, if one of these conditions were failing, we directly return false as the output. Now let's implement the same steps in a Java program. Coming to the function given to us, this is the function name and we are given the root of a binary tree. And the return type is a boolean, so we have to return either true or false as the output. Like we discussed, we are implementing this using BFS, so I'll need a queue. So declare a queue. This queue will contain 3 nodes. I'm going to name it queue and I'm going to implement it as a linked list. So initially I'm going to add the root into the queue. So queue.add of root, and I'm going to keep track of the level by using a variable called level, and the level is initially at 0. Now we keep iterating through the queue until the queue is empty. So the condition is that until this queue is empty, this while loop will run. And now for every level I have to keep track of the previous node, right? So that I can compare it with the next node inside that same level, so that I can implement these two conditions. If it is strictly increasing at even index, if it is strictly decreasing at odd index. So I keep track of a node. I'm going to name it previous node and initially it is null. And now let's find the size of the current queue. That is how many nodes are present in the current level. So I create a variable size and use the size method on the queue. Now let's iterate through all the elements inside the queue by using the size variable. So for every level, this size variable will keep on changing, and I use a for loop to iterate through all the nodes inside that level. Now inside every level, I have to keep track of the current node, so that I can compare it with the previous node. I'm going to name it current node and I'm going to extract the current node from the queue using the poll method. So this poll method will remove that node from the queue. So this poll method will return the first element from the queue and also remove it from the queue. And now we have to check if the current level is even or odd. So I keep track of the level variable, right? So I'm going to check if it is a even level by using the modulus operator. If it is 0, if the remainder is 0, then it is a even level. In the else block, we're going to handle the logic for odd level. So first in even level, we have to check that there are only odd integer values. So access the current value. So if this current node dot value, if you mod it with 2, if it leaves a remainder of 0, then it is a even value. So this is even level logic, right? So at even level, we have to check that only odd integer values are present. But if we encounter a even integer value, so we can directly return false. And now again, we have to check for the second condition where we return false, that at even level, the values are strictly increasing. We return false if it is decreasing order. So to check if this is a decreasing order, we use the previous node and the current node. So first we check if previous is not equal to null, because initially it is equal to null. And now we check if the previous node value is greater than or equal to the current node value. If this condition is true, then it means that it is in decreasing order, but we need strictly increasing. If it is in decreasing order, then we return false. So this is the logic for even level. Now in the else block, we have to implement the logic for odd level. So this will be similar. So I'll copy this and make some minor changes. So this is odd level. So if at odd level, like here, the value should be even. So to return false, we check if the values are odd. A value, when you do modulus operator, it leaves a remainder 1. If it is odd, then we return false. And we have to check if the values are strictly decreasing. So we do the opposite of that. We check if the values are strictly increasing. If previous value is less than or equal to current value, then it means that it is an increasing, but we need decreasing. If it is an increasing, we return false. So for example, if we are in the last level, this is the previous value and this is the current value. For the next iteration, when the current is here, previous has to become here. So update the previous node value. So previous node will become current node. And now we have to add the left child and right child for every node into the queue. So first we check if the current node has a left child. So if current node dot left is not equal to null, only then we have to add that value into the queue. So queue.add of current node.left. Now let's copy this and do the same for the right child. So if current node.right is not equal to null, then add current node.right into the queue. And now this for loop will handle the logic for one level. And before going to the next iteration, we have to increment the level, right? So initially level was 0. So before starting the next level, we increment level. And this while loop will happen for all the levels until the queue is empty. Now outside this while loop, if we never return false, then we return true as the output. Now there are a few typos here. This has to be previous node, and here also n has to be capital. Now let's try to run the code. The test cases are being accepted. Let's submit the code. And a solution is accepted. So the time complexity of this approach is O of n, where n is the number of nodes present inside the binary tree, because we visit all the nodes once to process them. And the space complexity is also O of n, because we're using a queue to compute the output, and all the nodes will be added into the queue. That's it guys, thank you for watching, and I'll see you in the next video.